So good morning. Welcome to the second part of the morning session. It's my pleasure to introduce the next speaker. This is Vinicius Albani, my colleague from my department, Mathematics department in Florianópolis, Santa Catarina. Vinicius is a former student of this house, IMPA, worked with George Zubelli. And today he's going to talk about optimal convergence rate results for linear inverse problems in Hilbert spaces. Please, Vinicius. Welcome.
So, thank you, Antonio. Thank you, the organizers. This is a joint work with Ottmar Scherze and Peter Elbau from Vienna and Martin de Hoop from Rice University. This is the outline. I will talk about 4 results on equivalence between convergence rates and some source conditions and variational source conditions. And then at the end, I will talk about saturation result. So the tools that we use, this is a linear inverse problem. L is a linear operator that is bounded. So, and we, of course, we are talking about a regularization technique. So we consider the data with noise. So y tilde is the data with noise, and x dagger is the minimum norm solution. So the first example is the Tikhonov regularization, and we can write the regularized solution in this way. So this is, we use this form of represent solutions to define more general regularization methods. And of course, this is a regularization technique, and we have this convergence when the noise level goes to 0 with an appropriate choice for the regularization parameter alpha. So more generally, we consider a regularization technique represented by this function R alpha. In the case of Tikhonov regularization, it's just 1 over lambda plus alpha. Lambda represents this operator. And R alpha is a continuous function that satisfies this estimate. So it's controlled by the 1 over lambda and by this constant rho over the square root of alpha times lambda. We also define this error function R tilde alpha, which is which measures the distance between your regularization operator and the identity. This error function satisfies these 2 estimates. When we take this as a function of alpha, so we replace alpha by lambda by alpha here, and we have these 2 estimates. It's bounded from below and from above. R tilde is also decreasing as a function of lambda and is increasing as a function of alpha. So what we want to do here is to state sufficient conditions to imply this convergence rate. This convergence rate in terms of some function phi. Phi is some abstract function. And there are a lot of different convergence rates. The most common are phi with the so-called Hölder decay. So in some cases, it's just delta to the power nu with nu between 0 and 1. This is the most common convergence rate. And E, capital E, represents the spectral resolution of the operator L star L. So we shall make use of this representation of the operator G evaluated at L star L. So now we have the first result. It's just the equivalence between the convergence rate with noiseless data and the asymptotic behavior of the so-called tail function. if the tail function has this behavior here, it's this decay, then we have this convergence rate and vice versa. So this is, there is a result from Neubauer in 1997 for the case of Tikhonov regularization and phi as a Hölder function that states a similar equivalence. But now we have this general setting. The proof is quite simple. For the first implication, it's just rewrite this estimate as the application of this R tilde in the L star L and write down this as this integral. So now, since this is a decreasing function, we just replace lambda by alpha and take this out from the integral, and we have this estimated. It's this lower estimate on this quantity here. So, by this hypothesis implies that this tail function has this decay. The converse is more involved. So what we do is to write again in this way, this estimate, and then integrate by parts and break in 3 parts. Then we estimate each one. The first one is just to apply this estimate on phi. And in the second one, we use this hypothesis here. The second and in the third one. Then we use the lower bound on R tilde alpha here. And again, we use the hypothesis and this estimates on phi. Here, we use this estimate here. So this is just the proof of this proposition, and then we apply this to the case studied by Neubauer. So this is the Tikhonov regularization function here, and this is the error function in the case of Tikhonov regularization. So it's bounded. If you replace lambda by alpha, it's just 1/4. And the hypothesis is it's quite easy to prove that it satisfies the hypothesis when we replace this R tilde alpha by this function and phi by this function, which is the Hölder, represents the Hölder decay. Then we recover the Neubauer result from 1997. We also applied this to the case of logarithmic source conditions. So we consider this logarithmic function, and again, Tikhonov regularization. And it's not so difficult to prove that phi and this R tilde alpha satisfy the hypothesis with the constant a equals to 1, and then we have this equivalence in the case of logarithmic decay. It was a problem that was open during almost 20 years, but we used just this integration by parts and solve it. In the case of noisy data, the problem is much more involved. We need more on the function phi. So phi must satisfy this condition with G some increasing function, and continuous, of course, and these two conditions. These are quite abstract conditions, but they appeared in the proof, so we needed to include this in the hypothesis. So we needed that to prove the theorem. But we shall see that it's not difficult to prove that in the case of logarithmic phi and Hölder phi, they also satisfy all these hypotheses. So it's, and of course, in the Tikhonov regularization case. To achieve the convergence rate in the noisy case, we need some additional function psi, which is defined in terms of phi here. And in general, we cannot find psi explicitly. We can only define it implicitly, but we shall see that in the case of logarithmic source condition, it's not so difficult to find a logarithmic decay here. The proof of this result is much more involved. So before starting to show the main steps to the proof, we choose phi and psi such that these two equations are satisfied. And the main step is the choice of the regularization parameter alpha. Alpha must satisfy this equation. And if alpha satisfies this equation, we have these two estimates, these two inequalities. The first inequality holds for any alpha, and this lower bound here only holds for alpha delta in the spectrum of L times L star. But we shall use this to prove that this condition holds for any alpha here. For this infinite. So, okay. So this condition on phi implies in this condition on psi. So in a similar condition on psi, so with a different g here. And to prove the first implication, we assume this. And using the fact that alpha delta satisfied this equation, so with alpha replaced by alpha delta, this is equals to that, and use this estimate to find this inequality. So by the definition of psi and some simple algebraic manipulations, we can find this here from this. And then taking the infimum in alpha and the supremum in y in some ball with radius delta from the noiseless data, we find this first implication in here. This first implication. The converse, we need more. Okay, converse here. So we need both inequalities in this main step here. So we first need the hypothesis and this lower bound in the main step. So by the definition of psi and this condition and some algebraic manipulations, we find this estimate. So recall that this is equal to this distance. So we can prove this, that this, here. We can prove that this implies in this estimate for any alpha in the spectrum of L times L star. To prove for any alpha, where is it? We use this to alpha minus and alpha plus and use this condition. So for any alpha, we have that this is equals to the sum of these two integrals and use this estimate here. So we use this, the inequality holds for this with alpha in the alpha plus in the spectrum of LL star and alpha minus in the spectrum of LL star. So we just use this. This is the proof of the main step. To the upper bound in the main step that we consider in the proof of this theorem, of this proposition. So we use this main step here to prove this, that this implies in both inequalities. The upper bound is not so difficult, so just use the triangle inequality and rewrite this second term as this scalar product, and we can find this bound. It's not so difficult. The main problem is to prove the lower bound, because we need to find a particular y tilde. That depends on this z delta, which is defined by this. So f is in the spectral resolution of L star. So that's why we must find this alpha delta in the spectrum and take this A delta in this interval so that this operator is not 0. So that's why Z delta must be non-zero, so for everything work. And take this supremum and y, and taking the infimum in alpha, we have this estimate. And since these functions are monotone, and we have this, it's domain, we have this lower bound of this term in alpha delta, and this lower bound in the terms. For example, here, if alpha is between 0 to and alpha delta, we have this lower bound. If alpha is between alpha delta and the norm of L, we have this lower bound. So both are this is proportional to this, and is also proportional to this. So we have the lower bound. And now we have this application. So if we replace the general regularization technique by the Tikhonov regularization, and the general phi by this Hurler function. So it's not so difficult to prove that phi satisfies this equation here. So the hypothesis on phi is satisfied, is fulfilled. And psi has an explicit form. So, and then we can recover the result obtained by Neubauer in 1997 for the case of noise data. So the equivalence between the estimate with noise data, the estimate with a noiseless data, and the estimate in the so-called tail function. Okay. We also can apply this to the case of Tikhonov regularization and a logarithmic function phi. And it's not difficult to prove that phi satisfies the hypothesis in the theorem. The only problem is with psi. We cannot find psi explicitly, but psi satisfies these two inequalities. So we can put this in the estimate here. So that's why we have the estimate with logarithmic function here. So we have this equivalence result with logarithmic decay. We also applied this to the case of these approximative source conditions or distance functions. So this distance function is just the distance between the x dagger, so the minimum norm solution, and the range, the image of this ball through this operator phi applied to the L star L. And assuming that phi is again an increasing continuous function with phi of 0 equals to 0, and satisfying this inequality, so instead of mu between 0 and 1, we just took mu equals to 1 over 2. Then we have this equivalence. So the convergence rate with noiseless data. So now we have this 2 to the power nu between 0 and 1, and the equivalence with this convergence rate with this distance function. The proof in one direction is not so difficult. We just use this triangular inequality here and use that this operator has norm less than 1, and use this inequality in the integral here. So we just write down this estimate as this integral, and using this estimate, we have this first one. So putting all together, we have this estimate. So taking the Hofmann and psi inside the ball, we have this estimate. And then to find the first implication, we just have to choose R appropriately. So R must be this. And assuming that the distance has this decay, we have the first implication. The converse is a bit more involved because we need to this operator. So since we took out the 0 here, it's invertible. So we define this psi alpha. We must prove that psi alpha is inside some ball with this R, and that this is dominated by this. So taking the Hofmann, so it's greater than the Hofmann of this quantity in terms of psi, we have this estimate. And if we choose R as this, we have that psi alpha is inside the ball. So we have the second implication. And again, we can apply this to the case of Tikhonov regularization and logarithmic and Hölder functions. We also found this equivalence between this variational source condition and the decay of the tail function. As in the last case, one direction is much easier than the other. So the first one is just write this as this scalar product and then you estimate. And then so use this again and use this estimate. And then just use the fact that this is an increasing function. So we have the estimate. But the converse is more involved because we need to break this scalar product into these two parts. The first one is easy to estimate, but the second one is more involved because we need this operator t, which is invertible too, because we took out the 0 because capital lambda is greater than 0. So it's invertible, and then we put it in this scalar product. And then break this in this norm here and this integral. Integrating by parts this part, we find this estimate, and this estimate is dominated by this. So we have this estimate. So to plug this and this to find this estimate here, we need these two conditions. This condition that this scalar product is greater than 1/2 this scalar product. And we can also prove that this scalar product is greater than this too, because this is right continuous and this is left continuous. And then using these two inequalities, we have this estimate, and using these two estimates, we have this. Again, we can apply this to the case of Tikhonov regularization and the Hölder function phi and the logarithmic function phi. And now we have this, in the end, we have this saturation result. So if the minimum norm solution is inside the range of this operator, so we have this behavior of the tail function. But this behavior of the tail function do not imply that x dagger is inside this range. We can only prove that psi dagger is inside the range of this operator with psi. Observe that psi is slower than phi when lambda goes to 0, because it's the power mu with mu less than 1. Mu must be less than 1. So this is not so difficult to prove. We just write down the inverse operator as this integral. and it's dominated by this, using this inequality. And integrating this by parts, we have that this integral is finite. If mu is equal to 1, it's diverged, it's infinite. So that's why x dagger cannot be in the range, in this range, sorry, if this holds. We only have this implication and this implication, not this, the converse here. And to finish, we just recall all the results. We found that the convergence rate with noiseless data is equivalent to this behavior of the tail function. And we have this equivalence between the convergence rate with noise data and noiseless data and the convergence rate with noise data. So here we have phi and here we have psi. We must be careful with that. Psi because it's not, in many cases it's not possible to find psi explicitly because it's defined in terms of this inverse function, the inverse of this function phi. And we have also proved that this convergence rate with noiseless data is equivalent to this convergence rate in terms of this distance function, which is given by this Hofmann inside this ball here. The distance of C dagger from the image of this, this ball through this operator. In addition, so phi must satisfy this condition too. And we have the equivalence between this behavior of the tail function and this source condition, variational source condition. And we had proved this saturation result. So this, we are trying to extend these results for some cases when, for example, the Hilbert space is replaced by Banach space, but it's much more involved because we lose a lot of machinery because the inclusion of the Banach space in its dual or in its bidual, it's really much more complicated than in the case of Hilbert spaces. And we are trying also to find in the case when we replace, for example, in Tikhonov regularization, but the regularization term by some Banach, like L1 norm. So, but it's also quite difficult to find some similar results in this case. So, thank you for your attention. I hope this will be interesting.